In this demonstration, I will show how to select among multiple models to forecast stock price increases. This is an example project for students. The idea is that we're going to take some data and from that predict stock price increases over time. So, if we look at a snapshot, a point in time, can we predict whether the stock price will increase over the next year or 6 months? So we're going to develop a price model that, given some rows of prior historical stock prices, we're going to predict some X increase. In particular, we'll choose 10% increase in price. So the inputs to our model will be a stock symbol, like this S&P 500 or NVDA, the percent increase in stock price that we anticipate, say 10%, and some forecast window. And this could be 6 months or a year or 14 days, something like that. The idea of this notebook is to illustrate the kind of notebook that students should structure their notebooks. And that is, there should be some introduction to the notebook showing an objective and some data set. Additionally, at some point, there should be a section on data processing where you download the data, check for the quality of the data, create some features, perhaps label the data, and if necessary, do some data balancing. Then at some point, we'll do a training of a model and summarize how well the model fits the data. And finally, we'll have an application of the model to predict, in this case, to predict future stock prices, as well as the conclusion of the overall process. So in this problem, we're going to take price data that has an open, high, low, close, volume, and a date for a symbol such as the S&P 500. And from these rows of data, we're going to predict whether the stock will increase over some period of time in the future. This will not be time series data, but just rows of cross-sectional data. We also, given our price data, we can compute some other features or indicators. So given our symbol, we can compute the 14-day RSI and a few other features here. We're going to use the Y Finance module to calculate these features. So given these rows of data, we're going to label the data indicating whether our classification of that stock is true or not. So given a row for today, we will label today's row true if sometime in the future the stock price increases by a certain amount. So if our data window is 365 days a year, for example, and our increase is 10%, then if today's row results in an increase greater than 10% 1 year later, and we know that by looking through the data, then we'll label today's row as 1, indicating it's true that the stock price is going to increase, and 0 if the stock price did not increase. So we're going to label the data based on our knowledge of future rows of data. This will be a logistic classification problem where, given a row of data, we're going to predict will the stock increase or not in the next time period. So in order to do this, we're going to train some models. For example, logistic regression, random forest, and a classifier, a gradient boost classifier. Once we have those trained on our data, which is our labeled data set, then we can select among them, in this case, a XG boost classifier seems to work best. We can also provide other ways to evaluate that: a precision recall curve, ROC curve, confusion matrix. And also, given the features we have, we can show which features are most predictive of the end result, which were the most important features. And then finally, once we have that model, just for fun, we can predict the future. So, for example, we'll have this output analyzing SPY, that's the S&P 500, predicting 0, meaning that it will not increase for the next time period. And we can do it by picking a number of rows. For example, let's take, the past 22 days and average those. And if it turns out on average they predict an increase, then we might suggest that the stock would increase. In this case, our result is based on the F1 metric of 0.96 in the last 22 trading days. The result is only 34% positive, so we suggest you do not buy. All right, based on this model, in fact, it was correct for the SPY that here's initial date and then a year later, and the increase was only 6% and not 10%. So in fact, it did correctly predict that there was not sufficient increase and you would not invest in it. Okay, so let's give this a try by running a demo and see what it looks like. So here's the model. Here's our notebook that's going to predict stock price increases. As I mentioned, this notebook illustrates the structure of a notebook that I would expect for student projects in general. It's going to use not time series, which might be better, but it's just going to use some cross-sectional data that is rows of data. It's going to build a model from that, and based on that, predict whether the stock will go up over a time period, say 365 days. Multiple models will be used, and then among them, the best will be selected. I got this idea from an interesting project called Predicting Future Stock Market Trends with Python and Machine Learning by Lucas Ray. If you look at this article, he talks about how to do what I'm going to do in this notebook. It's just in Python, though. It's not in PySpark. So we walk through, and I pretty much left his code as best I can as it is, but then modified it for PySpark and then ran multiple models and a few other things. But mostly the code is intended to be the same. So in the end, we're going to find out that this XGBoost classifier seems to work best. It correctly predicts the stock increases 90% of the time. And importantly, it does not give you a prediction of an increase when it's not the case, a false positive. And most it does it is, well, less than 5% of the time. In the example I provided, it's going to correctly predict the S&P 500 will not increase, and it will also correctly predict NVDA will increase. So a summary of what this looks like, and if you look in Databricks, you can see an outline on the left based on the headings that we have in our notebook. If we double click, we can see that we have markdown, and based on this markdown, it creates the headings that we'll see on the left. So we're going to take our data set, which is going to be rows of stock prices over time. We'll have a row for each stock price per day. Each row will be a day price. And we're going to use number of days to model and also predict. We'll download the data using Finance. We'll calculate some metrics using FINTA. And on Databricks, we're going to install this with pip install Finance in Finta. This uses some machine learning library, some deep learning, and you might need to install them. But if you just use the Databricks cluster, that has a ML in it, so they have different runtimes in Databricks, and if you choose one that has ML, then that will be the one you want, and it'll have the appropriate deep learning library. You won't need to install it. Next, we have some basic imports, and then some parameters like the number of days of download. Here we're just downloading 10,000 days of data. Interval is going to be 1 day. These are the indicators that we're going to apply to the stock in order to get some features. I left these exactly as they were from the original project. Some symbols that we could look at, for example, we're going to predict the S&P 500, Exxon, Apple, AMD, and NVDA. The two I'll focus on are going to be S&P 500 and NVIDIA. We can download the data and convert it to be a PySpark data frame. Here's the download of the data, and we'll create a Spark data frame from it. And what we'll do is for all of our stock symbols, we're going to go ahead and download and union all of the stock symbols into one large data set. It may be the case that we can predict our stock solely based on the stock features, but it might be interesting to include some economic features. And here I included some metrics about the 5-year bond treasury and 10-year treasury and 30-year treasury. And I forget one of the other ones. So these are some economic conditions. This is just for illustrative purposes. You can imagine importing the consumer price index and inflation and other economic conditions, include that in a row, and the combination of the stock information and economic information can be used to predict stock price. So that's what we have here. We've added our price data and joined it with our economic data, and now we have our overall data. Once we have that data, then we can go ahead and do some counts of NaN columns and null columns and so forth. Here you can see what it looks like when the data is downloaded. Same for the economic data. Now we've joined the data, and you can see there's a date, information about the stock, and then this latter columns are information about the economic conditions. They're the treasury yields. We can run a quality check and see that we've got a few rows that are, in fact, do have null values. We can summarize the data. And then here we'll aggregate it into some monthly data for plotting purposes. Now we go ahead and plot some charts about the data. This is distribution of closing prices. Here's closing prices per date. You can see that SPY is green and so forth. And then volume. And Apple has a big volume in this chart. So just some checks about the data. Now on to feature creation. It's indicated this Venta Python module has a bunch of calculations. I just took the original article and used those, but you can see it. The module supports lots. It says over 80 calculations, and here are some of those calculations. So we can use those as indicators. Here's the original function provided in the example project. Here's a way to get a schema, because we're going to use a user-defined function, a UDF, in order to calculate these. So this simply gets the UDF type information or schema. Now we're going to go ahead and create a UDF from the original given function called getIndicators, and addIndicators is going to be my UDF. And I use apply in pandas to apply it, and I specify the schema which is determined above. Once it happens, then we have all of our indicators for our stock by applying this applying this function as a UDF. It's called apply in pandas. That gives us our stock data. So our stock plus all of the associated indicators that we wanted. Now we're going to label the data, and we need to know what size window, how many days we're going to consider, what percentage, and if the current row increases by the appropriate percent within the window size, then we'll label it 1, otherwise 0. So we're going to use a window function in PySpark. We're going to partition by window, order by date, and the lead function will be used to look ahead a certain amount, window size amount. And if the increase is sufficient, that's what this calculation, P change, percent change, will calculate. If that percent change is greater than the change we want, then we're going to label our data as 1, otherwise it's 0. This is how we determine if the price current is in the future going to be an increase above what we want, which we currently specify 1 year and 10%. Based on that labeled data, now we can go ahead and look at our data. So we've got our different symbols and the label and the count, and we're going to determine whether our data is balanced or not. Since it's not 50-50, it's not exactly balanced. It may be okay, but we can improve on that by using class weights. In an earlier video, I showed how to calculate these class weights, and this is exactly the same code from that earlier video. And now we're going to go ahead and apply those weights. We're going to apply it to our data frame and our various stock symbols. And the idea here is that we're not going to average it across all the weights across all stocks. Each stock has its own weighting. So we're going to select the stock symbol, subset of the data, and then for that particular stock, we're going to go ahead and specify the weighted column. And then we'll do that through all the stocks, and then we'll end up with each stock having its own weights. We then look at the result of our symbol and the weight. You can see that the weights for the SPY, the S&P 500, have a different weighting than Exxon. So each stock has its own weighting. And if you want to go ahead and use the weighted data, which is I'm assuming here, then we'll go ahead and use that data frame. Otherwise, you could just fill in the weights as all being 1, and there would be essentially no weighting. But anyway, this notebook has it, so you can run either way. And right now, we're going to run it with the stock weighting. Okay, next up, we're going to create a pipeline. And if you looked at the previous videos, it's the usual sort of pipeline. We're going to look at all of our columns except we're not going to consider the date, the symbol, the lead, the percent change, the label, and the weight in our prediction of the future increase, which is specified by the label being 1 or 0. We have a pipeline, which starts out with empty. We have a base pipeline, which uses vector assembler to take all the other columns, put them in a vector features, and then run it through a standard scaler because the features have different scales, different units of measure. So we're going to run it through a standard scaler. The output will be features. And then those features will be taken by a number of alternative models: logistic regression, random forest, standard gradient boost classifier found in the Spark ML library. Also found in the deep learning library from Databricks is the XBoost classifier. So we're going to try this. So 2 different kinds of XBoost classifiers, or gradient boost classifiers. You can also consider using this multi-layer perceptron class. I left it in here, but it turns out it really doesn't work very well unless you increase the number of the size of the model, and it ends up being, for this small Databricks demo, it ends up being that it runs out of memory. So I've just removed that, but if you have a larger cluster, you might want to try it. In any case, it turns out these gradient boost classifiers seem to work best in any case. Right, next up, we're going to run our pipeline through a cross validator. We'll use a couple running at the same time, two parallelism. And I made this a little bit smaller, the 16 shuffle partitions, repartitioned into 16 because we have a small demo cluster, and if you have too many partitions, it ends up being a little bit slow. If you run all of this, it runs about 30 to 60 minutes, closer to 60 minutes. And if you note above, we don't have any parameters in our models. Now, you can certainly add parameters as well. It's just going to run a little bit longer. Okay, you can see here it took about an hour. Once it runs, then we can go ahead and see what our results were. The way that this runs is this cross-validate stock function runs the cross-validator, and it runs it for individual stocks. So just something to note, that it's going to run and train models based on an individual stock. So this model here, we're going to end up with a set of models. And in this simple case, we're going to run in NVDA and the S&P 500, and then all. And the idea is you're going to have a model just for the S&P 500 and just for NVIDIA. In addition to that, you're going to model all stocks. So the question here is it better to just have a general theory of stock price increase, in which case you look across all symbols, or do you believe each stock may react differently and you want to have an individual model for each stock? So we have both here. Each stock has its own model as well as one model for all stocks. And the way we do that is when we look at our data, you can see it only pulls out the data for one particular stock and trains the model only on that stock data. Whereas in the second case, we train the model on all the data. So the last model here, called all, will be taking all the data in order to predict stock prices. So we'll end up with models, one for NVIDIA, one for the S&P 500, and one final one based on all stock data. Once we've trained them, then we can see that for NVIDIA we had 4 models, and Spider we had 4 models, and so forth. And these are the different metrics used to determine how well they are. I think they're all F1. All right, so let's go ahead and plot them out. In prior videos, I show how to pull out the metrics. We're just going to plot them. And so you can see here are the models for NVIDIA: logistic regression, random forest, gradient boost from the Spark library, and then also the imported deep learning XGBoost. And you can see the last one does the best. We also have it for the SPY, the S&P 500, and also the XGBoost does the best. The last, predicting all stock prices. Again, the last XGBoost does the best. I've got sort of a long function here, and you can look at some of the details. I grabbed some code from some other people in order to print out some of the metrics, especially because some of the metrics are not easily had with the Spark machine learning library, but can be calculated. So calculated precision, recall, and so forth for XGBoost. That's what all of this does. Once I've got those functions, I can go ahead now and evaluate the best models. So let's go ahead and for each one of the models, see how well they did. And we're going to do take our best model in each case, that's the XGBoost, and transform it over the training data and the test data and look at those predictions. Based on those predictions, we'll evaluate them. In particular, I'm most concerned about the test predictions or the validation of them. So this is what we end up with. So the first one is the NVIDIA model, and then you can see a quick summary of the prediction recall area in the curve and ROC area in the curve, and there's an F1 score, and also you can set the beta, the ratio of the precision recall as half or 2, and come up with different values. In any case, here are a number of metrics and how well they did. And ignore this. I decided to block out this plot because it wasn't very interesting, so I left that plot out. But you can see a precision recall curve here, and then the ROC curve and confusion matrix. And you can see how well they did. In this case, we have some cases where the actual stock price did not increase 10%, but we did predict it did about 3% of the time, so that's not so good. But otherwise, we get actual increase being 0, and we predicted 0 57% of the time. Actual increase of 10%, we're correct 97% of the time in this case. This was all for NVIDIA. Okay, now we can also look at the feature importance, and I want to point out here that these numbers here with the underbar, these are the treasury yields, and I'm going to remove them in a moment and run the same thing again without this what I call the economic context. So in this case, the model relied on the economic context, the treasury yields, in order to predict the price, and it did okay, but we'll find out if we remove them whether it does better or worse. All right, next up, the S&P 500, same thing in terms of looking how well it predicts. You can see the precision recall curve, sort of okay, and ROC curves looks pretty good, and so forth. And once again, it's relying on some treasury information. Last one, this is predicting, it's modeling all of our, we only have maybe 5 stocks, but it's modeling them all, and then predicting based on that. And again, you can see the various metrics here, precision recall, ROC, and confusion matrix, and so forth, and feature importance. And once we have that, we can go ahead and say, okay, given these models, we can write a little bit of code here to go ahead and apply that model to some current data. Let's say we've built our model up, and now we want to know whether in the future the stock is going to go up. So let's take, say, the last 30 days, for example. And based on that, let's go ahead and transform, take our model and apply it to the last 30 days. And let's sort of look at the number of days at a percentage that's going to be increasing. So if our current data predicts in the future that the stock is going to go up, then we might buy it. And otherwise we wouldn't buy it. So we can do that prediction just based on one row. We could do it based on a number of rows here. So here we grab the most 30 rows of data, and transform our model over that data, get our predictions, and based on that prediction, we pick out whether it's a 1 or a 0, and if it's 0, then the stock is not going to go up 10% in a year, and if it's a 1, it is. That's the prediction. We could also look at the number of, if we have, say, 30 days, how many of those 30 days, most recent 30 days, does it predict it to go up? And if we say 80% of them have to say in the future it goes up, then we might make a purchase, and if it doesn't, if it's less than 80%, then we don't. So here's the result of it. This function here just says the calculation about the prediction to the existing data. And we're going to do it for all of our models that are not the all. So that basically means that we're going to have the NVIDIA model predict NVIDIA, and the S&P 500 predict the S&P 500. And And then the last case, we're going to do the overall market model and say this overall market model will predict the S&P 500 NVIDIA. So if you look at it here, the NVIDIA model, these are stock-specific models. It says here that the model has an F1 of 0.97. In the last 22 trading days, it's 100% positive. So we say it should go up by at least by 10%. In contrast, the S&P 500, the last 22 days, our F metric, our model is pretty good at 0.96. And it says 100% positive, and so we recommend you buy it, which is sort of interesting. And then the market model, NVIDIA. In this case, 100% for the last 22 days. The F1 is 96, 100% positive. We suggest you buy it. And then the last one is the overall market model again, 100% positive for the last 22 days, and it says to buy it. These are so all buys. And you can ignore this right now because it turns out the spider does not go up, but NVIDIA does. But this model, this result here is based on not including the economic forecast information, but just including the stock information. So let's run it again just to show how it works. In that case, by including the economic information, it actually did not have a good prediction. Let's go ahead and remove it. So here's her indicators. Let me go back to, here's the economic data. So this one turns out it does not work so well. So we're downloading it, which is fine. But this time I'm not going to include I'm not going to do the join here. Okay, so let's get rid of the economic data and just run the whole thing with just the price information and the associated indicators, and not include in the yields on treasuries. Now I've run it again, this time without the stock economic data. So previously in the example, we had these treasury yields at 10-year and 30-year and 5-year and so forth. They were included in the data. And they were also then included in the model, and the model then used this to help predict the stock prices. This time around, I wanted to go ahead and show the difference by removing them. So now we just have stock prices. Everything else now is the same. There's a few more rows of data because there was, about 80 rows of data that had some null values previously because of the use of the treasury amounts. But we've removed those, and then the remainder is the same in terms of the stock closing price distribution and price. Zoom in a little bit. And same indicators, everything just run is exactly the same as before. Same labeling and so forth. But this time there's no economic treasury information in it, the yields for the treasury bills. Okay, so now I run it through again, get different models. I mean, it's the same kind of model in that we've got a model for the NVIDIA, a model for the S&P 500, and a model for all stocks. And it still, this time, takes about an hour again, but this time that doesn't use the 5-year and 10-year and 30-year data. So the models are about the same in terms of the F measure as before. And if we look at the overall evaluations of these models, you'll see that it's a little bit better. So here we go with NVIDIA. So it only uses NVIDIA data. And now we have 0.2% for predicting an increase when there is no increase. That's this false positive here. And you notice that both of these are in the 90s, 98, 99 for correctly predicting increases and correctly predicting no increase. This time, the feature for NVIDIA, there's none of this treasury data. Instead, it's just some metrics associated with the stock itself. Those are the most important. Same with the S&P 500. And again, low number of predicting increase when there is no increase. So again, the metrics here, in terms of the most important, they're specific to the stock itself. And then here's the model for predicting all stocks based on all stock data that we have. It's again a little bit worse, but it's still better than when we included the yield data for the 5, 10, and 30-year treasury yields. All right, now we're going to apply the forecasting. Well, let's see, this time I hope the forecasting is a little bit better. So if we look at the stock-specific models, NVIDIA, past 22 days, the metric is 97, 100% positive, and predicting an increase by 10%. S&P 500, 18% positive. This is different than before. The F1 measure is 96, only 18% positive, so it will not increase. So this time we're recommending not to buy the S&P 500 based on this model that's specific to the S&P 500. Now, if we have our single market model, it's going to apply to all of our stocks. And again, it recommends that we do buy NVIDIA. And here it recommends do not buy the S&P 500. So in this case, removing that economic data, those columns associated with the treasury yields for the 5, 10, and 30, I believe, it is correct. That is, it does not recommend that you buy the S&P 500 over this period. And if you actually check it, you'll see that it only was up 6% and not 10%, so it was correct. And it did recommend that we buy NVIDIA. In fact, it was up over 85% over this period, so it correctly identified that. Okay, and you can go to Fred, for example, or your favorite site to look at the actual values. So conclusion of all of this, best classifier was, in all cases, was XG Boost classifier. Performs best with or without weights. You can try that as well. Correctly predicts stocks over 90% of the time, and incorrectly predicts an increase only about less than 5% of the time. How can we improve on this? Probably lots of ways, but what we can do is consider using time series data and perhaps other metrics. And I mentioned here interest rates. It turned out that didn't really work out so well, but you can consider other metrics and add them in. So there's a number of ways to improve this. So just a reminder that this was an introduction into how to structure your notebook. If you're trying to give an overview of what you're doing, you have some sort of introduction, specifically including the objective you're trying to determine, some description of the data set, then the data set processing itself, including feature creation, labeling if necessary, perhaps some data rebalancing. In our case, using weights, the model training and its associated summary, applying the model to the idea of models are predict things. So given some data, predict it, and some summary of the overall process. In this case, the overall process was that the XG Boost classifier was best, and actually did do pretty good at predicting, whether to buy some stock. In one case, recommending correctly to avoid S&P 500 and correctly to purchase NVIDIA. Okay, so that's an example project of stock prediction. That's the kind of project that my students do. And this shows you how to structure the notebook as well as how to run a few models in order to do your prediction. Hope it works for you.